This is the second part of chapter 30. Here we have the problem solving session. A toroidal solenoid with mean radius r and cross-sectional area is wound uniformly within 1 turns. This means that it has a circular cross-sectional area. A second toroidal solenoid within 2 turns is wound uniformly on top of the first so that the 2 solenoids have the same cross-sectional area and mean radius. What is the mutual inductance of the 2 solenoids? Assume that the magnetic field of the first solenoid is uniform across the cross-section of the 2 solenoids. If N1 is 500 turns and N2 300 turns, and the radius is 10 centimeters and A is 0.8 square centimeters, what is the value of the mutual inductance? Now, I will say the flux of one of them passes through the other, and therefore we have the magnetic field is going to be, let's say, created from B1 is going to be mu 0 N1 I1 divided by 2R. And I will say also, we can say that the mutual inductance, it is into phi, the flux, the magnetic flux for 2 divided by I1. Here we can start calculating what is really the flux. It is B1 times area, which is mu 0 N1 I1 A divided by 2 pi r, and I will say M is going to be based on this N2 times that flux divided by I1, then is going to be mu 0 N1 N2 A divided by 2 pi r. I can simply just plug in the numbers, but don't forget to convert the area into cubic square meters, and also the radius into meters. The answer is 24 microhenries. The inductor in the figure has inductance of 0.260 Henry and carries a current in the direction shown in decreasing and shown is decreasing at a uniform rate. Di over dt equals negative 0.0180 amperes per second. Find the self-inductance, the self-induced EMF, which end of the inductor A or B is at a higher potential. First, to calculate E, we know that it is L di over dt, and then it is 0.26 Henry times the rate, and that is 4.68 10 to the negative 3 volts. Now, for which end is the A or B is at a higher potential, we can say here terminal A is at a higher potential since the coil pushes current through B to A, and if replaced by a battery, it would have the plus terminal at A. Okay, another one. A long straight solenoid has in turns uniform cross-sectional area A and length L. Show that the inductance of this solenoid is given by the equation L equals mu 0 AN squared divided by L. Assume that the magnetic field is uniform inside the solenoid and 0 outside. Your answer is approximate because B is actually smaller at the ends than at the center. For this reason, your answer is actually an upper limit on the inductance. B, if we have a metallic laboratory spring that is typically 5 centimeter long and 1.50 centimeter in diameter and has 50 coils, if you connect such a spring in an electric circuit, how much self-inductance must you include for it if you model it as an ideal solenoid? First, for the first part, we know that n, it is the number of turns per unit length, then therefore it is n divided by L, and then L, it is n phi b divided by I. We know also that B, it is mu 0 n I for the solenoid, and then mu 0 n over L times I. Phi B, which is the magnetic flux, it is BA cosine 0. Then it is mu 0 n over L times I times A. And then L, we're gonna put this into this equation here, is gonna be n, sorry. It's gonna be come on, what's wrong? Right, I'm here. Then L, it is n mu 0 n I A L over I over Li, and then the I is going to cancel, and n times n, it is n squared. Now for the spring, we have L is 5 centimeters, the diameter is 0.510 centimeter, and it has in 50 coils. Then the area, it is pi r squared, which is pi, and we need to convert the centimeters into meters. Calculate the radius from the diameter, and then this is the cross-sectional area. Now L is gonna be mu 0 n squared A divided by L, and mu 0, it is the 4 pi 10 to the negative 7. The number of turns is 50, it is squared, and then we have here the area that we have calculated divided by the length. That's it for this question. Next. Here we have a 35.0 volt battery with negligible internal resistance, and we have a 50 ohm resistor and a 1.25 millihenry inductor with negligible resistance are all connected in series with an open switch. The switch is suddenly closed. This is a circuit that has R and L, RL circuit, and I will say how long after closing the switch will the current through the inductor reach 1/2 of its maximum value. Now I will say here, this is the circuit, and then I need to know how long we're gonna reach 1/2 of I maximum. The maximum current is gonna be when we have E divided by R, because like this equation is gonna be I equals I maximum 1 minus E minus T over tau. Tau, it is the time constant, and that is L divided by R. Now the maximum current occurs after a long time, and I max is it is E over R. Then I need to find what is really I maximum over 2 is going to occur when we have 1 minus E minus T over tau equals 1/2. If we take the natural logarithm of both sides, then we can actually say that this is going to be the time 17.3 microseconds. Now, part B is, sorry. How long after closing the switch will the energy stored in the inductor reach one half of its maximum value? We know at the beginning, okay, here that we have the current is gonna be the maximum, and then we can say that U is gonna be one half U maximum. This is what we are looking for, and that is gonna happen when I equals I maximum divided by square root of 2. And then here we need to find when this time is. Then we're gonna put 1 minus t over tau should equal 1 over square root of 2. We're going to take the natural logarithm of both sides and calculate the time. This is 30.7. Then the time in part A is 0.92, and for part B is going to be 1.23 tau, and that is a verification that we are doing the correct thing, because our tau here, it is L over R, which is 2.5 10 to the negative 5 seconds, which is 25 microseconds. A 15 microfarad capacitor is charged by a 150 voltage power supply, then disconnected from the power and connected in series to with a 0.280 millihenry inductor. Calculate the oscillation frequency of the circuit, the energy stored in the capacitor at t equals 0 millisecond, the moment of connection with the inductor, the energy stored after 1.30 milliseconds. An LC circuit, this is, oscillates with the energy going back and forth between electrical energy and magnetic energy. Electrical for the capacitor and magnetic for the inductor. We can calculate the frequency as omega over 2 pi, and here omega is 1 over square root of LC. Then we can combine the two equations. Then the frequency is going to be 1 over 2 pi 1 divided by 2 pi square root of LC, and then I will be able to calculate what is really the frequency. Now EC, the electric energy, it is 1/2 CV squared, and that is 0.169. We can calculate I, the current is sinusoidal, minus omega q sine omega t, and UL, it is 1/2 LI squared. Now we need to calculate first what is really the omega, which is the 2 pi frequency times the frequency, and sorry, wait. Sometimes it's jumping. Okay, then let's go back here. We have the frequency, and then EC, and then I, and then we were able to calculate what is omega, which is the 2 pi times the frequency. Then I will be able to calculate what is Q, which is C times V, and then I can be calculated using the equation and the angle here, it is, remember, it's in radians, and then we will be able to find what is really the current. And then finally I can calculate U as 1/2 Li squared, which is 0.148 joules. The next one, it is an 18 microfarad capacitor is placed across a 22.5 volt battery for several seconds and is then connected across a 12 millihenry inductor that had no appreciable resistance. After the capacitor and inductor are connected together, find the maximum current in the circuit. When the current is a maximum, what is the charge on the capacitor? How long after the capacitor and inductor are connected together does it take for the capacitor to be completely discharged for the first time, for the second time, and sketch graphs of the charge on the capacitor plates and the current through the inductor as functions of time. Then here I listed my quantities, C, L, the EMF, and then I listed also, I did draw the circuit. UL maximum, of course, equals UC maximum, and that is when we have L, UL maximum is going to be 1/2 Li maximum squared, and this equals 1 CV squared. Then I maximum can be calculated as C over L times V squared. Now then, based on the values, we can calculate I maximum as 0.871 amperes. The charge on the capacitor is 0 since all the energy now is for the inductor. Actually, this is what's happening with the circuit, and just like I want you to want to remind you with like this one here, it is the oscillating between electrical and electrical and okay, here just review this from the textbook where we have these conversions between electrical and magnetic energy. I think here I did a mistake in the circuit. Okay, just 1 second. Let me have this smaller. Yeah, I kept the battery here, and that is wrong here. A 18 microfarad capacitor is placed across a 22.5 volts battery for several seconds and is then connected across. That has, oh yeah, then I don't have that EMF, sorry. Then this is really here, there is a mistake in this circuit, like remove this EMF, this one here. I just noticed that. No, not all. Oh yeah, this one here. Just remove this, and just here, this one. Come on. here I will say remove the EMF. All right, and then I will say here the charge on the capacitor is 0, since all the energy now is for the inductor, and then we are going to have that switching between electrical and magnetic energy for the whole period, as was described before. Now we want to find how long after the capacitor and inductor are connected together does it take for the capacitor to completely discharge for the first time and for the second time. What we can do is we know that here okay, that the time that we're gonna have this, it is when it is 140 and 3/4 t, based on the diagram from the textbook, the one that was here, this one here. If you look at these numbers, this is here 1/4t, and here is gonna be 3/4t, and therefore we know that this is really the time, and then I can calculate the period, which is 1 over the frequency as 2 pi square root of L over C, and this time is 2.92 milliseconds, and then I can find what is 1/4 of the time, and I can find what is the 3/4 of the time. And then of course I know that the charge is gonna fluctuate between plus 405 and negative 405, and for the current between 0.871 and negative 0.871, and it has a sinusoidal dependence. Q0 here we can calculate as V times C, which is 22.5 times 18.0 microfarad, and that is 405 micro coulomb. Okay, then now here we have an LRC series circuit that has L equals 0.6 Henry and C equals 3 microfarads. Calculate the angular frequency of oscillation for the circuit when R equals 0. Then this is like the question before, omega equals 2 pi frequency, and that is 2 pi over T, and then it is 2 pi over 2 pi divided by LC. Then this omega, it is 1 over square root of LC, and that is 745. Now we know that when we have an R, that is gonna give the critical damping, and the critical damping is gonna happen when 1 over LC equals R over 2L squared, and then from that I can calculate what is the value of R, and it is 894 ohms. Then if I wish to calculate the oscillation frequency when I'm gonna have 1/2 R, then I can find what is really the 1/2 R, and then the oscillation frequency is going to be the angular frequency. Omega prime, it is the square root of 1 over LC minus R squared over 4L squared, and then R is gonna be the square root of L over C again, like if I equate these two here together, and then r squared, it is L over C, and I will say I can find what is omega prime, and from that I will be able to calculate what is really the here, what is really the value of omega prime. This is the last one, I believe. Here I have 44. It is a coil that has 400 turns and self-inductance 7.50 millihenry. The current in the coil varies with time according to I equals 0.680 amperes times cosine pi t over 0.0250 seconds. What is the maximum EMF induced in the coil? What is the maximum average flux through each turn of the coil at t equals 0.0180? What is the magnitude of the induced EMF? Of course, I listed here my quantities, and then I have that this is the expression for I, and then EMF is going to be minus L di over dt, and therefore I just here I can differentiate this, and then I will say it is negative 0.680 amperes pi over 0.02505 sine pi t over the 0.025, and then the maximum occurs when sine theta is 1, and then I will be able to calculate EMF as 0.641 volts. B is asking for what is the maximum average flux through each turn of the coil. I can calculate phi, which is Li maximum divided by the number of turns, and the number of turns is 400. Then I will be able to find what is really how many whippers per turn. I can also calculate E at that time, which is the 0.01805, and from the calculation I can have that as 0.494. Sorry for going up and down. I'm not used to using my computer, and thank you very much for listening.